So, 8.3. All right, in the previous two lessons, we talked about what vectors are, we talked about vector components, and we talked about addition and subtraction of vectors. Now, multiplication is an operation that exists for numbers, scalars, but it doesn't really exist in the sense that we know it for vectors. Instead, in vectors, we have what we call a dot product. Okay, so what is a dot product? A dot product is this. If you have two vectors like this, A and B, okay, and suppose you were to shine a light, like a flashlight, right here, so that, you know, you hold the flashlight perpendicular to B, right? Do you see that A will cast a shadow onto B? Okay? And the length of that shadow will be as long as that bracket is right there on the bottom. Okay? So this will be the length of the shadow that A casts on B. But this is math. We don't use shadow. That's not a very mathy term. Instead, we call it the projection of A onto B. So this is the projection of A onto B. All right? These need some vectors here. Vectors, arrows. Okay, now, so look at that projection. I can measure that projection with a ruler, right? And I get a length, a scalar value for the length. So now I have that projection of A onto B. That's a length. Now I can multiply that with the length of vector B. Okay? That's also a length. And when I multiply them, that number that I get from multiplying those two is called the dot product. We'll talk about application later, but that's what dot product means. Basically, the length of this vector times the length of the shadow that the other one casts on it. All right, so it's two lengths multiplied by each other. What that means physically, we'll do an example later on. Now, let's first talk about how we find a dot product. All right? To find a dot product, oh, and by the way, a dot product is written as A dot B, like this, and that's a pronounced dot, A dot B. Okay? All right, next. So we write A, we can write a vector in component form, right? A1 and A2. And we can write the second vector in component form, B1 and B2. Now, to find A dot B, what you do is you multiply the first components, A1 times B1. You multiply the second components, A2, B2, and you add them together, and you get that value. All right? So let's do an example of a dot product in this first example. So we need to find the dot product of U and V. We have to do U dot V. All right, so let's do U dot V. Okay. So let's find U dot V. This is going to equal the product of negative 3 times 3 plus 4 times 6. So U dot V, negative 9 plus 24, 15. And that's it. All right? That's dot product. It's a scalar, it's a number, period. Yeah.
So when you say U dot V, dot is not a multiplication sign, right?
No, it's not a straight multiplication sign like you are used to. Okay? It's a complete, like it's a different concept altogether. Okay, yeah.
Is that how we multiply vectors though?
Yeah, so there is no such thing as multiplying vectors. That concept doesn't exist. With vectors, there's addition, or in the subtraction is like a byproduct of that. There is dot product, there is cross product, things like that. There is no such thing as multiplying or dividing vectors. Those concepts don't exist. Okay, so now, look at this new term, orthogonal, right? Orthogonal is another word for perpendicular. So in geometry, two lines would be perpendicular to each other. And then there's also the term orthogonal. So let's think about that for a minute. What does an orthodontist do to your teeth? Straightens them. And what would an orthopedist do to your bones? Straighten them as well. So that ortho word must mean, you know, straight, right? And then what's G-O-N, like gone, like a polygon. A polygon has many, what? Many sides. So G-O-N, that's the meaning for side. So orthogonal, you know, is when, you know, the sides are straight, like perpendicular, all right? So that's what okay, so let's talk about orthogonal vectors. So now I have these two that are orthogonal, and suppose I cast my light like this, okay, perpendicular to the bottom vector. How much of a shadow is U going to cast on V? None. So if the dot product, if the dot product is the length of the shadow times the length of V, if the length of the shadow is 0, then what's the dot product? 0. Okay? So if an angle between two vectors is 90, okay, then there is no shadow, and the dot product will equal to 0. That's how you know if two vectors are orthogonal. All right? Okay. So take a look at this one here. Let's find the product of U and, or the dot product of U and V. So U dot V is 2 times negative 14 plus 7 times 4, 0. That means U and V are orthogonal. Okay. Huh? All right. Huh? All right. So, the dot product is commutative. U dot V is the same as V dot W. It's associative. Okay. If you have a 0 vector and the dot product of the 0 vector with anything else is 0. Okay. And then, okay, so what if you have a vector A? Okay, so remember, a vector has a specific magnitude and direction. And imagine now I have another vector A. What would that look like? It would look like this. And, you know, I'm going to put them side by side like this. Now if I were to shine a light onto the top vector A, how much of a shadow is it going to cast on the bottom vector? None? All of it, right? This is a big light. Okay, all of it, right? So now, if I want to talk about the dot product then, A dot A, it's the length of the bottom vector times the length of the shadow, which is the same. Right? So it's A squared. Okay? So it means, if you go here, I can take the dot product of a vector in itself, and if I take a square root of that, that's the magnitude of a vector A. Yeah.
So you said like so to find the dot product, it's the projection of A versus B times the length of B. But then
the magnitude of A. All right. Let's see what A dot A is. It's a dot.
They're those.
Huh?
The ones in the top. Like A.
The
Are those
is
A times A?
Yeah, that's a multiplication, but the rest, it's a,
I was just trying to
yeah.
differentiate.
Yeah. So normally, when it's a scalar, right, that's multiplying numbers. But when it's a vector, it's the dot product. That same symbol is used with two meanings. If it's used for scalars, like these two are scalars here, it's just the length. When it's used for scalars, it's the same as multiplying, 8 times 3. But when you use it in connection to vectors, then it's dot product. Okay. So what's A dot A? That's A dot A, right? So that will be -6 times -6 plus 5 times 5, 51. No, 61. And now, that's A dot A. Now, if I take that number and take a square root, guess what I got? Magnitude of A.
You could have also.
You could have also done it the other way. Exactly. I'm just showing that that's the exact same thing. Okay? Yeah. All right. So let's talk about how we find the angle between two vectors. Okay? Here I have vector A and vector B, and they're joined by an angle A here, or through an angle A. All right. So now I want to find an expression for that angle. Okay? Theta. So first let's talk about what A dot B is, right? Where does A dot B come from? Okay, so we said A dot B was the projection, let me do this in color, the projection of A onto B. And where is that? That's this length, right? Times the magnitude of vector B. Okay, the length of vector B, and that's that, right? Okay, so how do I find that red distance? Let's think about how we find that red distance. If I know A, and how am I going to relate those two? Can I say cosine of theta is the projection over A? Does that make sense? Right? Is the cosine of theta this red over A? Yes? Yeah? Okay, so then how much is the projection? It's magnitude of A times cosine theta is the projection. Okay? So now let's come back here. A dot B is equal to, how much is the projection? It's A cosine theta, right? Times the length of B. So now, what's A dot B? If I write A and B closer to each other, it's A, B, cosine theta. Now, if I want to solve for cosine theta, what do I do? I have to divide by what? AB. So cosine theta is A dot B over A times B. Okay? So you need to know that formula. You need to be able to use it, right? It's the same formula as you're given here. And then, I just do this so you are, you better understand, so that you understand better where it comes from. Yeah.
I understand that A dot B is not multiplication.
So in this case, what's the difference between A dot B and A times B?
Okay, so A dot B is the distance of this red. So if I measure this with a ruler, and I get, let's say, 15 centimeters, and then times that, and I get 29 centimeters. That green times red distances, that's A dot B. Okay? And so how did I find that? That's the magnitude of B, right? Times that red distance. How much is that red distance? If you ignore that green, how much is that red distance? Cosine okay. Let me stop this for a minute. Triangle between vectors u and v. So let's see. Cosine of theta is going to be u dot v over magnitude of u, magnitude of v. Okay, so let's find all of these parts separately. First, I want to find u dot v. That's 1 times 2 plus negative 4 times 6. That's 2 minus 24, negative 22. That's u dot v. Now, what's magnitude of u? 2 squared. 1 squared plus 4 squared in a square root, root 17. Right? So what's magnitude of v? Root 4 plus 36, root 40. Now, you're going to use these in the intermediate steps, so let's just leave them like this for a minute. So now, cosine of theta is equal to, put each of these into this formula now, just plug them in. So I have negative 22 over root 17 times root 40. Okay? Yes? So now, if you go in your calculator, what do we have there? Negative 22 over, negative 22 over the square root of 17 times 40, right? I can combine the roots. And that's negative 0.8437. Okay, so then what's theta? Yeah, inverse cosine of that number. So, whoops. So how much is that? Right? You always do control answer, right? Never the abbreviated. So it's, I'm in degrees. I'm sorry, I'm in radian. But how much is it in degrees? 147 point. Is it? Oh, so it's 147.5?
Yeah.
Okay, so let's think about what that means. Degrees, right? So let's think about what that means for a minute. If I have an x and a y axis here, let me draw vector u and vector v. Where is vector u? It's 1 comma negative 4. 1 comma negative 4. So there, right? That's vector u. Where's vector v? 2 comma 6. Here. Right? So what have I found? I have found that that angle in between is 147.5 degrees. Does that make sense? Is it reasonable? Does it seem reasonable? It does. Yes. No, it's not the direction of any of them. It's the angle in between the two vectors. Well, the direction, that was a different formula. Remember, it was the tangent of theta. You would have to do it for each of the vectors. It was tangent of theta equals y over x. Okay, so take a look at this next one now. You have, okay, it says to find the angle between the vectors in radian. Okay, so look at what we have here. I have vector u. It's cosine of 7 pi over 6 I hat plus sine of 7 pi over 6 j hat. Okay, what the heck is that? What is cosine of 7 pi over 6? How much is that?
That'd be 1/2.
Negative root 3 over 2, right? Because it's 7 pi over 6. And what about the sine? Negative 1/2. So what we have here, don't let the sine and the cosine fool you. All you have, because cosine of 7 pi over 6, it's just a number, right? Okay, so it's like if you ate half a pizza, and I asked you, hey, how much of the pizza did you eat? And instead of saying a half, you say sine of 30, right? So don't let the sine of 30 fool you, or don't let the cosine of 7 pi over 6 fool you. That's just negative root 2 over 2, or root 3 over 2. And the sine is negative 1/2. So if I were to draw that vector u, what would it look like? I go to the left, negative root 3 over 2, and down negative 1/2. That's like something like that, right? Is that something that is reasonable for vector u? Yeah? I think so. And what about vector v? What's that look like? What's cosine of 5 pi over 4? Negative root 2 over 2. And the sine? Negative root 2 over 2. So if I were to draw that, is that, reasonable? Yeah, that's reasonable for v. And so what is it that I want now? I want the angle in between. So hey, you know what? Why don't I draw these together? Why don't I draw u, right, together? I'm sorry, here. And now, how much is the angle from here to here for u? How much is that angle? 7 pi over 6, right? Does it make sense to you that that's 7 pi over 6? Okay, so now let's draw v. V, we're going to go left root 2 over 2, down root 2 over 2. So that's going to look more like that, v. How much is that angle for v? 5 pi over 4. Okay, if I want the angle in between, right, then the angle in between is that little part right there. Okay? So, I wouldn't have any problem if, I took a simpler case where I had,
It's good like that, promise you.
an angle of 75 degrees and an angle of 30 degrees, right? Could I find the angle in between here? I would just subtract them, right? Well, can I do the same thing over here? Yes, I can. So theta is 5 pi over 4 minus 7 pi over 6.
Why is it the same thing?
5 pi over 4 is bigger. It goes further. So 5 pi over 4 minus 7 pi over 6.
Is we got a calculator for it?
Oh, no.
No, I don't need it.
And it's pi over 12. Okay? So, did we have to do anything fancy schmancy? We did not. We were fooled at the very beginning, but then we realized, oh my gosh, that's like not even a thing. Okay, so why do we use dot product? Where do we use dot product? Why do we need dot product? Well, I will tell you. do you remember a long time ago when we did section 1, there was this guy, Will, and he was digging in his garden. Do you remember that? And we said he was exerting a force with an angle of 70 degrees and like it was, you know, into the ground. And I showed you guys that example of if I were to push a table horizontally across, right? Would I like bend down and like push horizontally? No, I would extend my arms, right? Hold the table, or, you know, if it's a chair, then it's a chair. I would hold it at an angle, and then if I push at an angle, the chair moves horizontally, right? Okay, why is that? Because as I'm exerting the force, there is a part of vertical component that's pointing down, but there is also a horizontal component that's pointing horizontally, and that component of the force is what's responsible for pushing the chair over, right? So, if I were to push directly down on this, that's how you can prove it. If I were to push directly downward, would the chair move forward? No. Why does it move magically? What's so magical about pushing it at an angle then? Well, that's because there is a vertical and a horizontal component, right? It's all vectors. You've been doing vectors since you were like yay big and you didn't even know about it, okay? And so now we come to how much work is being done, okay? Work, when you are very, very little, at the beginning, we say work is force times distance, but that's not the full story. Work is really force dot distance, F dot D, because in order for work to be done in the physical sense, in order for work to be done, you have to take the component of the force that's in the same direction as where the object is moving. So if this is moving horizontally, then only the horizontal component of the force contributes to the work. Okay. So, here, a person is pushing a box with a constant force of 40 newtons at a constant angle of 45 degrees. So here there is a force vector, and that's 40 newtons, and there is an angle of 45 degrees. Okay? So, in order for me to calculate the work being done, so it says find the work done in joules to move the box 12 meters. So this is moving this way 12 meters. What I need here is to calculate, is first to note the vertical and the horizontal components of the force. Okay? So this green is the horizontal component of the force. How much is that horizontal component? How did we find horizontal component for the quiz? It's F cosine. It's F cosine 45, isn't it? Okay, so I can rewrite this as the distance times F cosine theta. Work, sorry. The work remember how we said the work is F dot D? Well, okay, so we're only taking the horizontal component of the force, so it's F cosine theta. Okay?
Why only the horizontal?
Because in order to calculate work, you have to have the force that is in the same direction as the motion.
Where's the D?
Whatever direction the box is moving, you take that component of the force. If the box is moving horizontally, you take the horizontal component of the force. Okay, so now work is the force times 12 times cosine of 45. And who's going to plug that in for me? $339.4, and the unit here is joules. It's Newton times meter, which is a joule. Okay, so now, had we taken the entire force of 40 times the distance, how much would that have been? 480. That's a whole lot more, right, than the 340 units of work that's being done. Okay, so that's one way of calculating this. Now remember, this is a dot product. Another way of calculating it is using components. I could have given you the same information in component form. So why don't we take a look at that? Why don't we look at method 2 here? Okay, and let's use components. Can you write the force in component form?
Yeah.
How? Tell me.
40 cosine, 45.
Right, so the force is 40 cosine 45. Oh. 40 sine 45. And then what's the, somebody else, component form for the distance? 12 comma 0. So now, if I were to find work as force times distance, and if I were to do a dot product, how would that work? That would be 40 cosine 45 times 12 plus what? 0 times sine 45. Okay, 40 sine 45. So look, that would go away. So you still end with 12 times 40 cosine 45. Isn't that cool? So, right? So it's the same exact thing as if you do it that way or that way.
Wait, so for dot, it's not the projection. It's like there's no projection, is it?
Huh?
It's because it's this way and this way. How is there like a
Because one is horizontal, so that one component cancels out.
So you end up getting 40 times 12 cosine 45.
No matter which way you do it. Which means, on a test, hypothetically speaking, like in a couple of days, hypothetically speaking, I could give you the force like this. Or I could say, hey, there is a force component, 40 cosine 45, 40 sine 45, and a distance component, 12 comma 0, how much work is done? And you're like, oh yeah, that's the dot product. Yes? Yeah? Say yes. Yes.
Yes.
Okay, now, this is due Wednesday.